At everyday scales, the world feels solid, predictable, and continuous. A ball rolls because it is pushed. A car slows because of friction. A lamp shines because electricity flows through it. For centuries, classical physics described this world with remarkable success. It explained planets, machines, falling objects, lenses, and waves on water. But when scientists began looking closely at matter and light at extremely small scales, especially around atoms and subatomic particles, the familiar rules stopped working. The tiny world did not behave like a smaller version of the large world. It followed patterns that seemed strange, mathematical, and deeply unintuitive. Quantum mechanics is the theory built to describe that world. It is not a side branch of physics. It is one of the basic foundations of modern science. The key idea is that quantum mechanics describes the behavior of matter and light where classical physics becomes incomplete. Classical mechanics works beautifully for ordinary objects because their quantum behavior is hidden by scale. A chair, a planet, or a falling stone is made of quantum systems, but the collective result looks smooth and predictable. At atomic scales, however, the hidden structure becomes visible. Electrons, photons, atoms, and molecules do not always have properties that vary in a smooth, continuous way. Their behavior can depend on probability, measurement, and discrete allowed states. This is why quantum mechanics is needed for quantum chemistry, quantum technology, quantum information science, quantum field theory, and even areas like quantum biology. It gives scientists the language for nature's smallest machinery. One of the first shocks of quantum mechanics is quantization. In classical physics, many quantities can change continuously. A car can drive at almost any speed between 0 and its maximum. A ball can have a wide range of energies depending on how fast and how high it is. But quantum systems often allow only certain specific values. An electron bound inside an atom, for example, cannot simply have any energy it wants. It must occupy allowed energy states, like a musician only being able to play certain notes on a fixed scale. This does not mean the electron is literally a tiny musician or a ball sitting on a shelf. It means the mathematics of the system permits only particular outcomes. Energy, momentum, angular momentum, and other quantities can become discrete rather than continuous. This idea was not invented because scientists wanted reality to be mysterious. It arose because experiments forced them to rethink the rules. Around 1900, Max Planck studied blackbody radiation, the light emitted by an idealized hot object. Classical theory predicted results that did not match observation, especially at high frequencies. Planck found that the problem could be solved if energy was exchanged in small packets rather than in any arbitrary amount. These packets were later understood as part of the quantum idea. At first, this may have seemed like a mathematical trick. But it opened a door. If energy came in units, then the old assumption of smooth continuity was not always true. The microscopic world had a structure classical physics had missed. A few years later, Albert Einstein pushed the idea further with the photoelectric effect. Scientists knew that shining light on certain materials could cause electrons to be emitted. Classical wave theory suggested that brighter light should eventually provide enough energy to release electrons, regardless of frequency. But experiments showed something different. Low-frequency light could fail to eject electrons no matter how intense it was, while higher-frequency light could eject them more effectively. Einstein explained this by treating light as coming in packets of energy related to frequency. These packets are now called photons. The photoelectric effect showed that light, normally understood as a wave, could also behave as if it arrived in particle-like chunks. This was not a minor correction. It was a major crack in the old picture. That crack became one of quantum mechanics' most famous ideas, wave-particle duality. In the quantum world, matter and light can show characteristics of both waves and particles depending on how they are observed. Light can spread, interfere, and diffract like a wave, yet also arrive in individual photon events. Electrons can be detected as localized impacts, yet under the right conditions they create interference patterns associated with waves. This does not mean particles are secretly switching costumes between wave and particle. It means the classical categories are too limited. Quantum objects are described by a deeper mathematical structure, and the familiar words wave and particle capture only parts of their behavior. The weirdness is not just in the objects, it is in the inadequacy of everyday language. The modern form of quantum mechanics emerged in the mid-1920s, when scientists such as Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born, Paul Dirac, and others developed more complete mathematical frameworks. Schrödinger introduced an equation involving the wave function, a mathematical object that describes a quantum system. The wave function does not usually tell us a simple story like, the particle is exactly here, moving exactly this fast. Instead, it contains probability amplitudes. These amplitudes can be used to calculate the likelihood of different measurement outcomes, such as possible energies or momenta. This was a dramatic shift. Physics had long aimed to predict exact motion from exact starting conditions. Quantum mechanics replaced that expectation with a theory where probability is built into the foundation. Probability in quantum mechanics is not just a sign of ignorance in the ordinary sense. If you roll a die, probability often reflects not knowing the exact throw, angle, speed, and surface conditions. In principle, classical physics imagines that enough information would let you predict the outcome. Quantum mechanics is different. Even with a complete description of the system, the theory often gives probabilities for what a measurement may yield, not a single guaranteed result. Max Born's interpretation made this central. The wave function gives the mathematical basis for predicting probabilities. This makes quantum mechanics extraordinarily powerful, because it predicts statistical patterns with great precision. But it also challenges the older dream that nature must always be predictable in the direct, mechanical way familiar from large objects. Another central idea is the uncertainty principle, associated with Werner Heisenberg. It is often misunderstood as a problem caused merely by bad instruments. The real point is deeper. In quantum mechanics, certain pairs of physical quantities cannot both be assigned arbitrarily precise values at the same time. Position and momentum are the classic example. The more precisely one is known, the less precisely the other can be known in the quantum description. This is not just because measurement disturbs a tiny particle, although measurement can matter. It reflects the structure of quantum states themselves. A sharply localized wave-like state necessarily contains a spread of momenta, while a state with sharply defined momentum is spread out in position. Uncertainty is woven into the mathematics of the theory. Measurement is one reason quantum mechanics feels so strange. In ordinary life, measuring something seems passive. A thermometer reads temperature. A ruler reads length. We imagine the property already existed exactly as measured. In quantum mechanics, measurement is more subtle. The theory tells us how to calculate possible results and their probabilities, but the act of measurement selects an outcome from those possibilities. This does not mean reality is imaginary or that anything can happen. Quantum predictions are highly constrained and experimentally testable. But it does mean the relationship between a quantum system, its mathematical description, and the observed outcome is not as simple as the classical picture. The measuring process becomes part of the physical story, especially at microscopic scales. Although quantum mechanics sounds exotic, it is not detached from real life. The ordinary world is built from quantum systems. Chemical bonds depend on quantum behavior. The structure of atoms, the colors of materials, the operation of semiconductors, and the behavior of lasers all require quantum explanations. Modern electronics, medical imaging tools, solar cells, and communication technologies depend directly or indirectly on quantum physics. Quantum information science goes even further by using quantum states themselves as resources for computing and communication. The theory may feel abstract, but it is one of the reasons modern technology exists. Classical physics still works as an approximation for everyday objects, but underneath that approximation is a more fundamental quantum layer shaping what matter and light can do. The most important lesson of quantum mechanics is not simply that the universe is strange. It is that nature does not have to match human intuition. Our intuition was trained by medium-sized objects moving at ordinary speeds, not by electrons, photons, or atomic energy states. Quantum mechanics shows that at small scales, reality is governed by discrete states, probability amplitudes, wave-particle behavior, and unavoidable uncertainty. Yet this strange theory is not vague. It is mathematically precise and experimentally successful. Classical physics was not destroyed, it became a large-scale approximation of a deeper framework. Quantum mechanics changed science because it revealed that the familiar world is only one layer of reality. Beneath it is a smaller, stranger, and more fundamental order. If you found this helpful, please like this video and subscribe for more explainers.